Today we're going to do the uniformly accelerated motion worksheet. So we're going to start off by putting our name here. Oh no, my pen is not working. Try a different pen. Put your name and your number. And we have a position and time data table right here. So the first thing that we're going to do is consider this data for the wheel that's rolling from rest down an inclined plane. We're going to use the position and time data in the data table to first plot a graph. So remember that you need to plot position and time and label it properly. Consider which is going to go on the x-axis and which is going to go on the y-axis. Remember that our first data column here is our independent variable, and then our second one is our dependent variable. So think about which axis you're going to put each of these on. You should put time down here. Don't forget to label it properly with the units, and position over here. Again, don't forget to label it properly with the units, and then you need a title. Now, as you're figuring out your scale down here, you don't have to use the entire grid, but you should spread out your data so that it takes up most of the grid. Go ahead and do that now. All right, so now you should have graphed it, and you should have points that look something like this. What you want to do next is draw a smooth curve that shows that relationship, and your curve should pretty much go through your points. This is perfect data. It isn't, you'll notice that the lines fit perfectly. So you don't really have any variation. Now we go to the next page, and we just keep following the directions. So you'll see that it says complete the blank column in your data table, which allows you to straighten your graph. So we look back here at our shape, and we look at this shape. Take a second to think about what you would do to this line in order to straighten it. What you should have found is that you square the time axis, or square the time data. So we're going to make a data column with t squared and seconds squared, and go ahead and fill in those numbers. Should look like that. All right. Now, our next step is to plot the new graph on the axis to the right, and we need to label it properly. So we're going to make our linearized graph. We're going to put time squared on the x-axis, and then position on the y-axis. And you need to make this graph, you'll have to rescale the time axes so that you can fit up to 36 seconds there. And remember to make that scale be uniform. A common mistake is keeping the same spacing for the data points here and putting on the x-axis and putting like 1, 4, 9, 16, 25, 36. But remember that each box needs to represent the same number of seconds. So go ahead and do that now. And then your next step is to write your mathematical model for this graph. Don't forget to label it too. Okay, next part is the tricky part. We're going to be drawing some tangent lines. A tangent line shows the slope of the line at that point on a curve. So we're going to draw 5 tangent lines on our position versus time graph, and we're going to find the slope of each of these lines, and we're going to use that to fill in this data table. So let's go back to our position versus time graph. You have a nice curve here, and you'll notice that our curve changes slope as time goes on. And a tangent line shows the slope of the line, or of the curve. So what you're going to do is take your ruler and you're going to put it up to your curve so that it touches the curve in one place. It doesn't cross the curve. So like this would not be a tangent line, and this would not be a tangent line. It just touches in one place. And basically what that's doing is we're going to try to draw a line that touches that curve in one place and therefore shows what the slope of the line is at that point. So you can see that I've drawn this green tangent line. It touches my point at 1 second. And it only touches one place. It doesn't cross over. So at 1 second, I can say that my curved line and my green line are basically parallel. They have the same slope. So if I find the slope of this green line, then I can use that to know what the slope of my position versus time graph is at 1 second. And we know that the slope of a position versus time graph is velocity. So by finding the slope of this green tangent line, I can find the velocity at 1 second. So let's go ahead and do that. I've drawn this line. Now I'm just gonna find 2 points where it actually crosses the little hatch marks. So it looks like it crosses right there pretty nicely. And then it also crosses at my data point. So then I can do my slope is equal to change in y over change in x. And so my y2 is 1, 2, 3, 4, 5, and each one, so that's 0.25. And then I subtract y1, which is 0.05. And then I divide by my delta x, so my x final is 3.6. And my x initial is 1, excuse me. So then I get 0.2 divided by 2.6. And if I do that on my calculator, I can find that my slope or my velocity is equal to 0.076, so we'll do 0.08 meters per second. These are both in meters and these are both in seconds. Oh no. All right. So that's my velocity at 1 second. So then I go back here to my data table and I say at 1 second, my velocity is 0.08 meters per second. Then we're going to do that again. I think it's easiest just to do it at the certain times, but you can do it wherever you want. So let's use red this time. And I'm going to do another tangent line at 4 seconds. So I'm going to take my ruler and bring it up to the curve so that it's just barely touching the curve at 4 seconds. And then I'm going to draw my line. And this line is representing the slope of the curve at 4 seconds. So now what I can do is find my slope of this red line. So I take 2 places where the line crosses the hash marks perfectly. So I'm thinking right there and right there. And I can do my slope is equal to change in y over change in x. So my change in y, I get 1.65 minus 0.8 over change in x. So this is at 6.4 seconds minus 4 seconds. So I end up with 0.85 over 6. And I get that my slope, and this is in meters, this is in seconds. Oh, 6. Man, I wish I could do math. 2.4. 0.85 divided by 2.4 is 0.35. So my velocity is equal to 0.35 meters per second. And that happens at 4 seconds. So I go back to my data table and I put 4 and 0.35. I'm going to do that 5 different times. So you'll have 5 different tangent lines on your graph, and you'll have 5 different slope calculations. Once you do that, you will have a velocity versus time graph, or velocity versus time data table. And then on this, this thing right here, we're going to make a velocity versus time graph. So we'll put time down here, it's kind of scrunched, and velocity here. And then you also want to write the mathematical model for this graph. So go ahead and draw your tangent lines, find the slope of your tangent lines and the place where those tangent lines are tangent to the curve. Use this data to make a velocity versus time graph, and then we'll keep on moving. All right, the next thing we're gonna do is draw some secant lines. So you'll see that on number 8 it says on the position versus time graph, draw a line that connects the data point at t equals 0 seconds to t equals 6 seconds. Calculate the slope of this line in the space below. So we go back to our position versus time graph, which should have your 5 tangent lines on it, and it should look something like that. And you're going to draw a line, a secant line. Now a secant line intersects a curve in 2 places. So we're going to draw it from 0 seconds to 6 seconds. So you line your ruler up with those 2 points and you draw this line, and then you want to find the slope of that line, which you can do. Don't forget to use your scale as you do that. Number 9 says draw a point which connects 2 and 4. So we're going to draw another secant line. This time we're going to line up our ruler with the dot at 2 seconds and the dot at 4 seconds, and then we're going to draw another line. And then you want to find the slope of that line. So those are your secant lines. Go ahead and do that, and then you'll see that number 10 says to draw a line tangent at 3 seconds. You may have already done that, and if you've already done that, then you'll save yourself some time, and you need to find the slope of that line. Then you'll compare those 3 slopes and consider number 12. So why don't you answer those now? The next part is average velocity and midpoint time. This part is a little bit challenging, so I'm going to do it with you, or at least get you started. So if you go back to your data table, you'll see that there are spots that are offset, and this says delta t. So what this means is the change in time between this row and this row of data. So if you have 0 and 1, your change in time is 1 second. Then this one is for this row of data and this row of data. So the change in time between 2 and 1, 2 minus 1 gives you 1. You can do the rest of those. The next data column is change in position. And change in position, you're looking at the change in position for this one between here and here. So 0.05 minus 0 gives you 0.05. Then this one, you have the change in position between here and here. So 0.2 and 0.05. So you get 0.15. You can do the rest of those. Next, we have to do average velocity. Now we know our equation for average velocity is change in position over change in time. So that gives us our equation for average velocity. So to find your average velocity, you should take your change in position and divide by your change in time for each of these little sections of motion. So each one of these sections represents 1 second. So we're just going to do 0.05 meters per second, 0.15 meters per second, because we're dividing by 1 second. The time midpoint is challenging. You should have learned from your secant lines part that when the object is traveling with a constant acceleration, when you calculate the average acceleration over a given time interval, the instantaneous velocity is equal to that average velocity halfway through the time interval. And you should have seen that when you did the secant lines. So we need to figure out when the object is traveling at 0.05 meters per second. To do that, we're going to calculate the time midpoint, or the midpoint time. So this is the time that occurs halfway between this and this. So halfway between 0 and 1 is 0.5 seconds. Halfway between 1 and 2 is 1.5 seconds. So go ahead and take a second to finish your data table. The next step is to use your midpoint time and your average velocity to make a velocity versus time graph. I don't need to put graph in the title. So take a second to do that. Before you do that, do you think that this velocity versus time graph will look the same or different as this other velocity versus time graph that you have already made? So go ahead and make that prediction now. Now you've got some questions to answer on the motion of the wheel and your slopes and your y-intercepts. Remember when it asks about the significance of the slope of a graph, think about the units. And our goal here is to develop some of our general physics equations. So when you're developing the general physics equation, remember that you're going to start off with y equals mx plus b, and then instead of putting a y, you're going to put whatever's on your y-axis. Instead of putting m, you're putting whatever your slope represents. Instead of putting x, you're putting whatever's on your x-axis. Instead of b, you put whatever your y-intercept represents. And when you combine that all together, you'll get an equation that only has physics terms in it, which we call a general equation. All right, let's do the last couple ones here. So when you're finding what the area under a graph represents, you're going to use your units. And if we were to find the area of a shape, let's say the area of a rectangle, we would take length times width. So as we're doing that calculation, if you're doing this with a graph, you're going to take the units on the x-axis and y-axis and multiply them by the units of the x-axis. And that's going to give the units of the area under the curve, and that will help you determine the meaning of the area under the curve. The next thing on number 25, it asks you to draw a velocity versus time graph for an object with an initial velocity that is not 0. Now you are just sketching this graph, so you don't have to put numbers with it, but it'll help you do this part. So if we make this down here 0, 0, I need to have a velocity initial that is not 0. So maybe my velocity starts here at v initial, and then I accelerate at a constant rate to this v final, and then we can think about this shape where this is t. What is this shape right here? Do you remember the equation for this shape? This is a trapezoid, yes, and you can write the equation for the area of that in several ways. You can think about it as just a trapezoid, where we have 1/2 times base 1 plus base 2 times height, where this is base 1, this is base 2, and this is height. And you guys can plug in the appropriate things that represent those. Or you can think about it as a triangle and a rectangle. So you could have area equals 1/2 base times height for the triangle, plus length times width for the rectangle. And then you could plug in the appropriate physics terms on that one. One more comment here. Number 29 asks you to derive from equations 22 and 25. So that's the equation you get here and the equation you get here. And your goal is to find an equation that does not have time in it. So since you're trying to eliminate time, you'll want to use substitution and solve one of these for time and then plug it in to the other one, so that you have an equation that does not have time in it.